Okay, we're ready. Welcome everyone to the second Elixir Community Kraków meeting hosted by Software Mention. I would like to start with a few technical details for the guests at the office. If you want to take some cold beverage, you can go to the kitchen behind my back, and the refrigerator you will find cold beverages. And if you want to use bathrooms, they are next to the elevators outside the office. Welcome everyone. This is the second edition of our meeting, and I hope you will enjoy it. We will start with the presentation of my colleague from the Membrane team, who will be presenting by product created during the development of Membrane framework. Michał, you can continue.
Thank you, Bartek, for introducing me. Hi, everyone. My name is Michał. I'm a software engineer on WebRTC team in Membrane framework, and this is measuring beam performance using BEAMchmark. The outline of the presentation is as follows. So we are mostly going to talk about two things. The first one is Beam itself. We'll dive a little bit into the Beam internals. We'll discuss how Beam works under the hood. And the second one is BEAMchmark, of course, which is a tool that we created in Membrane framework for comparing performance across two different versions of your Elixir or Erlang application. I'm hoping to have a mixture of some introductory content as well as some slightly more tricky knowledge, so hopefully there is something for everyone. To begin with, let's consider a very simple scenario in which we have Elixir application that generates pretty big load. Therefore, we decided to do some profiling. There are plenty of already existing tools that you can use for profiling, like eProof or eProof. You can generate some flame graphs. So let's assume that we did some profiling. We also did some optimizations to our code. And the question is, how can we know whether those optimizations introduce significant performance gains? The first thing that might come to your mind is, hey, let's just check CPU load. And we will see whether it is higher or lower after introducing our optimization. And that's a pretty good idea. However, in case of Erlang virtual machine, it might not be a fully reliable metric. And to understand why CPU load might not be a fully reliable metric, we have to dive a little bit into the Beam internals. So let's start with the Beam architecture. The following figure presents simplified Beam architecture. The main entity here is a scheduler. So scheduler is something that is responsible for choosing process for execution and executing it. In fact, this is a little bit more complicated because it's an emulator who executes the process, but for this presentation, we can assume that scheduler does both of those things. Using the default Beam settings, we will run a separate scheduler per operating system thread. So assuming we have, for example, a CPU with 4 cores, 8 threads, we'll run 8 schedulers. In Erlang, in general, there are no threads, there are only processes, but those processes are much different than operating system processes. So they are very lightweight processes. Creation and deletion are very lightweight. We can create millions of such processes. And the first thing, very important thing here that we can see looking at this diagram is that we have a mapping one-to-many. So one operating system thread can run multiple Erlang processes. This is important because when we are switching between those processes, we don't have to perform context switch, operating system context switch. So we don't have to go into the kernel mode and go back to user mode. There are basically 3 types of schedulers: normal, CPU, and I/O. So maybe let's start with the CPU and I/O schedulers. They are responsible for executing long-running nifs and bifs mainly. We'll go to nifs and bifs later, and normal schedulers are responsible for executing casual Erlang code. The next thing I thing that is very important is scheduling. There is a book called the Erlang Runtime System book written by Eric Stenman. And in this book, we can read that scheduling in Erlang is, can be described as preemptive scheduling on top of cooperative scheduling. So what are those preemptive and cooperative schedulings? Preemptive scheduling is a scheduling where we have a scheduler who is responsible for choosing a process for the execution, executing this process, and deciding when to suspend this process and give control to some other process. So there is no cooperation from the process side in this mechanism. On the other hand, in cooperative scheduling, scheduler is limited to selecting some process for the execution, but it's process responsibility to give control back to the scheduler. So you can imagine that if we had a malicious process who loops forever, it will make our scheduling mechanism misbehaving. Therefore, this technique is called cooperative because processes has to cooperate with each other to make the whole scheduling process work properly. The question here is why we have combination of those two in Erlang. So in Erlang, we still have a scheduler who is responsible for selecting some process for the execution, but the interruption can be made at certain points, for example, when calling a function or when going into the receive block. Therefore, processes have to be written in a certain way that allows for interruptions. The nature of Erlang code is that you can almost not loop forever. If you want to simulate a loop, you have to use recursion, so this is a function call. And if you go to the receive block, which is blocking, you by definition can be suspended. In this way, Erlang scheduling is also cooperative. The question here is when scheduler can interrupt our process, and the answer is that our process can be suspended at 2 points. The first one is when the reduction counter for our process goes to 0, and the second one is when you go to the receive block and there is no matching message in the inbox. So maybe let's talk about reduction counter. What are reductions? Well, I haven't found exact definition what reduction is. However, at least each Erlang function call can be counted as one reduction. So when our scheduler chooses our process for the execution, it sets reductions counter to, I think, 4,000. And when our process uses all of these reductions, it will be suspended and the control will be given to some other process. The problem here is that with beefs and nifs, because beefs and nifs are functions that are, the definition is provided in Erlang, but the implementation is provided in C. So whenever you call such a function, reduction counter will be decreased by 1. However, we are not able to count reductions on the C side. So badly written beefs or nifs can make our scheduling mechanism misbehaving. Also, prior to R16, the beefs, I think very important beefs like binary to term and term to binary were non-yielding, and they counted as one reduction. So binary term and term to binary are beefs used for serializing Erlang terms into the binary format. And when you pass two big structure, two big Erlang map or list prior to R16, it could make our scheduling process misbehaving. The question is, how can we deal with this? There are 3 solutions. The first one is that we can try to chunk our nifs. In general, it's a good practice or in general, there is a general rule that our nif shouldn't take more than 1 millisecond of time. So if this is possible, we can try to split our nifs into smaller chunks that take not more than 1 millisecond. The other solution is to use dirty CPU and I/O schedulers, which I mentioned before. So those schedulers are dedicated for executing long-running nifs. And the third solution is to use yieldable C functions. So what are those yieldable C functions? Maybe let's start with yielding cfun. So yielding cfun is a tool provided by Erlang, which allows for generating yieldable version of your C code. Yieldable version of your C code works in the following way. In general, our function cannot or does not return in the middle of its execution. So when we call some function, it will return after it finishes its work. However, when we have yieldable version of our function, it can return in the middle of its execution and schedule itself for later continuation. And in the Erlang repository, I couldn't find documentation deployed online, but when you go into the source code, you can find a tool called yielding cfun, and this tool is responsible for converting your vanilla C code into yieldable version. At the moment, at least listed functions are implemented using yieldable C functions. So for example, when you are inserting something to ETS or when you are using some functions on maps, even quicksort is implemented in yieldable version and used in Erlang term to binary. And because this should be pretty simple, we can take a look at how usage of such tool looks like. So when you go to the Erlang repository, there is this tool yielding cfun, and we can go to examples. There is very simple example that implements SAH cryptographic algorithm. So what we have here, this is standalone Erlang project that implements some nifs. So we can go into the CSRC, there are our C code. And what you can see here, we have our nif code and SAHA2 directory in which we have our vanilla SAH implementation. When we call make here, what we can see is that we are going to call yielding cfun tool, which is used for generating yieldable version of our SAH function. So when we list once again files, you can see that we have some generated files. And when we take a look what is in our nif code, so in our nif code there is one main function called SAHA nif, and it basically calls this generated yieldable version of our cryptographic algorithm. When we are calling this function, here we are passing number of reductions that can be executed during or inside this function. And when this function ends, we are checking whether we should yield. So whether we should give control back to the scheduler. If yes, well, then we are scheduling execution or continuation of ourselves, and we are just giving control back to the scheduler. So that's how it looks like. The other way of interrupting our process is when we go into the receive block. So we can take a look at the process state machine. I think that this is maybe not, maybe this is pretty obvious. However, I think this is also worth mentioning. So whenever our process is running, it's in state running. So our scheduler is executing this process. And when we go into the receive block, we'll transit to waiting state. When we go to receive block and there is no matching message in our inbox. So we'll go to the waiting state. And when there is incoming message, we'll transit to the runnable state and then to running once again. So I'm mentioning about this because Gen server call is implemented under the hood, like it is calling a send to some process and then it is going into the receive block. So when we are doing a Gen server call, we'll will go into the waiting state for a while. Scheduler will stop executing our process, and when there is a response, we'll go back into the runnable queue, and scheduler will pick us later. The very last thing that I want to mention before going into the BEAMchmark topic is busy waiting. So what is busy waiting and why is it important? When scheduler runs out of work, it might be better to do some empty work than going to sleep. And this is because it might be better and it might help us to provide better responsiveness. This behavior is, of course, configurable with a proper flag in Erlang. We can even delete it or disable it. There is also something called scheduler utilization. So scheduler utilization is a metric that tells us how much given scheduler was running some processes. Assuming that we are benchmarking our Erlang virtual machine for 10 seconds and scheduler utilization was about 50%, this means that scheduler was executing some process code for 5 seconds. This scheduler utilization doesn't include busy waiting, which means that it can be lower than CPU load. Because CPU load, of course, will include busy waiting as we are consuming some CPU cycles, but scheduler utilization will not include this. The other interesting thing is that scheduler utilization can be also higher than CPU load. And this is because when a scheduler waits or is waiting for some I/O devices or I/O access, it is considered busy because it is not able to perform any further jobs. However, we will not use, in such a case, CPU cycles. So CPU load can be lower than scheduler utilization. So this was the first part of the presentation in which I wanted to show you that looking at one metric might not be the best idea in case of Erlang virtual machine. This is because of busy waiting. This is also because of reductions. It's also important in my opinion that to have pretty deep understanding of how Beam works under the hood. For example, because of dirty schedulers or long-running nifs. So finally, we can move to the BEAMchmark. And BEAMchmark is a very simple tool created in Membrane Framework for comparing performance across two different versions of your application. And I think that the best way would be to write a very simple example in which we will show the API, in which we will see the API of BEAMchmark. First of all, we have to install BEAMchmark. If you are writing very simple Elixir script, we can do this with Elixir mix install. So let's write mix install BEAMchmark. This should install the latest version of BEAMchmark. Next, we can define some very simple module that will generate some load on our machine. So we can benchmark something. And this module is called scenario, and it has to implement behavior called BEAMchmark scenario. And we have to implement only one function here, which is called run. And let's do some pretty straightforward operations just to generate some load. So let's generate some enumerable. And let's do some pretty obvious operations. We'll just use integer power function. And that's basically it. So this should generate some load. We just need to run this stream, and we are ready. And now we can call BEAMchmark. So we can do BEAMchmark run. we have to pass our scenario, some simple scenario, and now we can pass some configuration options. The first one is delay. So what is delay? Delay is used for, or should be used for warm mapping our Erlang virtual machine. This is important because in general, it's not a good idea to benchmark our application just after starting it. We need to allow JIT to do some work. We need to fill some caches. So we'll delay for 5 seconds. And we'll benchmark for, let's say, 15 seconds. And we can also provide some formatters. I think that we'll use HTML formatter. And the only option that we are going to pass here is auto open. So we'll see the result of running our benchmark automatically when it finishes its job. OK, so let's try to run this. You can run this with Elixir benchmark API access. And as you can see, we are first running a scenario, then we are waiting for 5 seconds, and then we are benchmarking for 15 seconds. Okay, and here we are. Here is our report. So at the beginning, we have some information, system information, like which Elixir version we are using or how many cores we have. We have also some configuration options. And then we have metrics. In metrics, we have the reductions number, context switches, and average CPU load. We have also some metrics related to or grouped by scheduler type. So we have utilization for CPU, schedulers, normal schedulers, IO schedulers. We have also weighted utilization, which is average scheduler utilization comparing to the CPU available time. And plots. Here are some plots of scheduler utilization and CPU usage. Those plots are, of course, interactive, so you can, for example, display only one usage only for one core. You can also zoom in, zoom out. You can download this as a PNG file. When you run benchmark for the second time, it should also compare results with the previous ones. So we'll see this in a while. You can, of course, disable this behavior. In such a case, benchmark will not compare results. I have also prepared real use cases of benchmark, so we'll discuss them in a while. So as you can see, we have run benchmark for the second time. We have also some comparison. We can notice that in this case, the CPU usage was about 8% higher. We have also some comparison on plots. And that's pretty much it. From other options that you can specify when running benchmark, you can also specify some name for easier distinction between different scenarios. And you can also disable comparing. As I said, I have prepared some real use cases of benchmark, so let's take a look at them. Here is example report from benchmarking our product, which is a video conference system. In this scenario, we had 6 rooms. In each room, we had two active speakers and 15 observers. So we have something around 100 participants. For each participant, we spawned multiple Erlang processes, and we are comparing behavior of this system using 2 different membrane core versions. As you can see, the version of membrane core without optimization was slower for about 30%. And what is interesting, when we take a look at the plots, we can see that all schedulers were running. So I think that we are using something about 51, 52 schedulers using the old version of membrane core, and something about 38 or 39 schedulers using the new membrane core version. And this is pretty interesting because, as I said, we had multiple processes per one peer, and we had over 100 participants. So you could expect that we will use all schedulers. This was running on a machine with 32 cores, 64 threads, as you can see here. And the reason why it is displayed like this, well, to know that, we have to go back to the Beam internals. And this is because scheduler load balancing. So let's go back to the presentation. Here are some tips that I was describing during running the BEAMchmark and scheduler load balancing. So the idea is that you will get better performance through better memory locality when processes are on the same CPU. And the result of this is that we are trying to compress work on as few schedulers as possible without overloading any CPU. Techniques for achieving this are mostly task stealing and migration. However, we will not discuss them here. You can read more about them in the Erlang runtime system book. And I think that's actually pretty much it. This was the usage of BEAMchmark API. The roadmap for BEAMchmark is pretty short at the moment. The only thing that we are going to do when it comes to metrics is memory consumption, and probably nothing more at the moment. Going to the summary, some conclusions from this talk. I wanted to show you that measuring Beam performance requires from you deep knowledge about Beam itself. And it might not be a good idea to take a look only at one metric like CPU load. I think that it's also important to put as many metrics in one place as possible because it's easier to see some correlations. Like when you see also that, for example, you are not running all schedulers, you start asking questions, so you go into the Beam itself, you start reading and you start understanding more. So I think that's all from me. At the end are also some resources I was using during this presentation. And thank you for your time. If there are any questions, I will be happy to answer them.
So I'm wondering how you would test some system that's actually undergoing some longer level, more long-time job. So you said that you were testing membrane under load with some calls happening, but the approach you showed was more about testing like a batch job that you just run from the shell, basically. So how would you go about? How did you go about testing such load of the system?
So one of the features we are going to add is ability to attach to a process. So for example, when you have already running system, you can attach to it and benchmark it for some time. In our case, where we have a Phoenix application, we are just starting it with BEAMchmark. So when you run BEAMchmark, we are just setting in configuration files to run a server. And that's how we start the whole application. We are also using delay for setting the conference room. So we are, for example, setting delay to 10 minutes. And at this time, we are creating rooms, joining with participants to the room, and stuff like this. But I think that the good approach for this would be to add a feature that will allow you to attach to already existing process. So you will set up your machine at first, and then you will attach a BEAMchmark to running system.
Okay, if there aren't any other questions, well, thank you, Michał. Just you can add one more thing. How can we find BEAMchmark?
Yeah, so BEAMchmark is available on GitHub under Membrane Framework Organization. There is no link, unfortunately, in the presentation. But when you type BEAMchmark in Google, I hope it will appear.
Okay, thank you very much.
Thank you.
Okay, now is the time to switch to our second guest. Yeah, our second presenter is Radek from Erlang Solutions. He's a tech lead over there, and he will be presenting about Gradualizer and gradual typing in Elixir, which I think is an interesting topic for anyone that have to deal with Dialyzer and its suggestions. So we'll just need a minute to set it up. And yeah, and it seems ready. Yeah, okay, so the stage is yours.
Możemy zaczynać. Okay, thanks for having me. My name is Radek Szymczyszyn, and I would like to say a few words about what's new in Gradualizer, and about gradually typing Elixir and Erlang. But first, one or two words about me. So I'm a tech lead at Erlang Solutions. I'm a static type system enthusiast. I'm actually one of the Gradualizer core team members for some time, and I'm also a co-creator of Gradient together with Przemek Wojtasik, who is our colleague from the Erlang Solutions office in Kraków. I'm also a believer in good quality docs, so I'm one of the co-authors of Erlang Enhancement Proposal 48, together with Jose Valim and Eric Bailey from the LFE community. And I'm also the implementer of this specification, this enhancement proposal in eDoc, which became part of OTP 24. And thanks to that, we can generate Xdoc documentation, so Xdoc static HTML docs for from Erlang projects. And more professionally, I'm an XMPP engineer. I have worked for a number of years with Mongoose IAM, which is our XMPP server written in Erlang, which is quite scalable, reaching, well, depending on the Amazon node we choose to run it on or to test it on, up to 2 million concurrent connections. So not bad, I guess. And today I would like to demo Gradient, which is mostly a front end to Gradualizer for Elixir. So there are some hoops we have to jump when we want to use a tool for Erlang with Elixir, but thanks to the same core representation, so the fact that both Elixir and Erlang compile to the same abstract format, we can do it. And Gradient is a tool that aims to like minimize the hassle, make the jumping the hoops as easy as possible. But maybe also a word about static type checking first and gradual type checking. So basically we have the distinction between programming languages, between dynamically typed programming languages and statically typed programming languages. So dynamically typed programming languages are those where the invalid operations are detected at runtime and they lead to runtime exceptions. So we write some code, we have to run it, and if the code is buggy, we'll only know because a runtime exception is thrown. Well, ideally in our tests, but sometimes in production. Statically typed programming languages are those where we just won't be able to compile some piece of code if it's buggy, where buggy is actually depending on the type system used in a particular programming language. So the benefits are that we get the feedback earlier, and quite often we get very precise feedback about what's wrong and specifically where it's wrong in the program. So having said that, let's just jump to the demo. Okay, I hope the font is big enough, so we'll work with that, but please let me know if it's too small. On the left-hand side, I have an editor open with the demo server. On the right-hand side, I just have an Elixir shell open where we'll be type checking this. So maybe let's start with just that, with type checking this file. And we got feedback that it's okay. So there are no type errors detected. And we actually don't have to run it. We just run the type checker on it. And what is the code about? So quite often we model our activities in Elixir or Erlang applications as processes. And one of the most common patterns is to use a gen server. So it's basically the skeleton of a server that we fill in with the specific logic of our application. So the skeleton means that it will receive messages, it will respond to these messages, and depending on the type of, well, the callbacks we implement, these might be synchronous messages or asynchronous messages. And here in this example server, we declare the type of the messages it's going to receive. So if you're familiar with Elm, for example, you might recognize the pattern that we define an abstract data type with some variants, and every action that our code does, or every action that somebody can like run on it from the outside, is declared by this data type. In our case, this is a contract about handling an echo request and a hello request, which are very trivial and defined in a module outside this example. So let's see what happens. Let's just see what happens when I change this contract declaration to something like this. I will run the type checker again, and we get feedback that the clause on line 63 cannot be reached. So let's go there and see what's there. Here we have the standard handle call, which basically implements the code for handling one of the requests, the hello request. And apparently, it cannot be reached. So this code will never be called. It will never be used. So okay, let's fix that. Sorry. Let's type check again. And good, fine, fixed. So let's check another scenario. We go back to the full definition. So we have two types, the echo request contract and the hello request contract, but this time they are expanded. So I just don't use references to external types, to remote types. I use them inline. Let's see what happens now. And we get feedback that there are non-exhaustive patterns on line 58. So let's jump there and see what's going on. And this is our first clause of the handle call function. So we get feedback that this function will be called with a value, with the example here on the right-hand side. That's a tagged tuple with hello and some binary. And we get feedback that this function is expected to handle this, but it doesn't. So like we have missing implementation. Like for example, we expect the server to do something, but we forget to write the implementation. And we get feedback about it before even running it. So not bad. At this point, what else can we get out of this? For example, or maybe not, maybe let me fix that first before we proceed. So I implement the missing functionality, run the type checker again. Okay, back to normal. So far so good. What else can we do with it? Can the type checker help us with something else on the implementation side? So let's try doing something like this. For example, I made a silly mistake when implementing this code. I made a typo, so it's different than the protocol, than the declared messaging interface. Let's type check it now. And we got feedback that this pattern, echo rex, on line 58, doesn't have the type message. Well, which is true, it doesn't have this type, because I made a stupid mistake when typing. So let's also fix that. And back to normal. So what do we get from running this tool on our code? We get dead code elimination, or we find dead code. We find the code that's missing, so missing implementation, and we are also covered in case of silly mistakes like typos and stuff. So sounds good to me. But what else can we use it for? For example, this was the core or the internals of the server. What about the caller side? So the process that actually sends a message to our server. Can this type checker help us in any way on this side of things, of the interface? So let's imagine that similarly to the type of requests, we could also define a type of the response. And for example, the response also might have different variants depending on what's happening on the server side, for example, some internal state. So we can define this response to be of type contract hello res, so response. And if we do that, we also get the benefits of type checking on this side of things, on this side of the interface. So let's for example do something like this. Again, do a silly mistake in our hello function and type check that. And we get the feedback that the pattern OKZ is not of the type of the expected response, which is again true. The thing here though is that specifying this type here is completely on us, like on me, the programmer. I cannot do a mistake here, because if I do, the type checker won't be able to help us. So we have to help it help us. And one more thing that's important, why it's the case, is that if we look at the help of this function, we see that GenServer call actually returns term. And term is the most general type in the entire type system. Like, it can be basically anything. That's why we have to provide this extra information here. Okay, so this syntax though might be a bit confusing. So the annotate type with the response type being passed as an argument. So I was showing before, we can also refactor it similarly to how it's done with the hello request, like this. This already feels more like usual Elixir code. But if we still don't like it, we can do something else. We can just define an auxiliary function called call echo, and in our case it would look like this. And in this case, the information about this type that we have to provide, so contract echo res, is included in the spec file. So the gist of doing that is that we have to pass this information to the type checker somehow, either through this annotation or through this spec attribute, which is also a kind of annotation. The thing that happens at runtime, so gen server call, is exactly the same. And the annotate type macro we see here actually doesn't do anything at runtime. The only thing it does is it leaves information about this type in the abstract syntax tree of the program for the type checker. And that's really it about the first example. So I'm wondering if there is any question at this point. Okay, so I'll proceed to the next one. So we could also ask ourselves the question, how else can we use the type checker, or how else can it help us? What else can it check before we run the program? So in an Elixir system, we have these processes, but they are different. Like one process can handle messages of a certain type, another process will handle messages of a different type. So one thing that we could do is try to use the type checker to protect us from sending a specific kind of a message to a process that simply doesn't know it, doesn't understand it, cannot do anything useful with it. And here we try to do something exactly like it. So first, let's look at the test, because it will help us understand what's going to happen and how to prevent it. So I will just run it. And in this case, it returned payload. Then I uncomment a code that's broken and run it again. And let's see what happens now. We see it blocked. And we don't know why. And after a while, it timed out. So the gen server call timed out. So let's see what the test does to understand what happened. But it's important to know that it happened at runtime. We had to run it to actually get this error. So in the test, we start our server, whose speed is stored under the variable srv. And we also start or spawn a completely different process that obviously will not handle the same messages as our server. And then when we use the API defined in our servers module with the server, it works, it returns payload. But when we use this API with some ordinary process, some random process, well, we saw what happened. It crashed at runtime after the timeout. So can we use the type checker to prevent something like this from happening? Let's see. And indeed, when we type check this file, we get the feedback that on line 103, the type that's expected is T, but we pass an ordinary PID, which basically means that we try to use the API of our specific server with a random process. And it's good, because this time we got this feedback just by running the type checker, not when running the code, so not in tests and not in prod, but ideally on our working machine. So how is this achieved? Basically, similarly to the protocol that we declared in the previous example, we also declare the type. The type is just a T, as is the usual convention. We define it to ultimately be a PID, but in this case, it's the PID of our specific process, our specific server process. And later on, all the API functions that we call, instead of returning a PID, return our T type. So startling does it. Echo function, the echo API function accepts that instead of a PID. And
basically all the public, all the exported functions do the same thing. And thanks to that, it's impossible to misuse the API of this particular server with a different process, because the T will be just a different type for every server that we define. And again, one more benefit from using the type checker on our code. So any questions this far? I guess not. So let's go to the last example, which is stage 4. And let's go to the echo function and see what can we get from using Elixir macros, a little bit of macro magic to make this even more type safe. So in the first example, we talked about the auxiliary function called echo. And when I was showing this demo to Robert Virding, he immediately spotted that, but well, we have everything we need to actually generate this function. So we don't even have to write it ourselves. We can just do something smart to have it generated for us. And indeed, that's the case. So in this example, we call this function, but we don't define it ourselves anywhere. Here we have it commented out. It's exactly the same definition that is actually generated, but we don't have to write it ourselves. And let's see if it works. For example, if I do something like this, just so that I'm not showing something that's broken. Yeah, it detects the error. I fix the error. It compiles. No problems with that. Okay, so how do we achieve this generation? Basically, on this side, so in the implementation, we use something like typed server reply. Instead of using gen server reply or the return values from a handle call function, we explicitly call typed server reply. And one more thing that's a bit different from the previous example is that apart from the value of the response, we also provide the type of the response here. So in the first example, we had to provide the type at the, let's say, call site where we were sending the message. And here we provide this type next to the actual value. So the locality is way bigger, is way better. It's harder to make a mistake if we have the value and the type next to each other. And let's see what happens if we, again, make a mistake in the value and it's not what it should be. And in this case, actually because we use this typed server reply macro, we will also get feedback if these things don't match. So in the first example, it would be on us. If I made a mistake, well, I might figure out, the type checker might find it, or it might not. In this case, with this auxiliary typed server macro, it's asserted that the value is actually of the type that we provide later on. So let's fix that. Type check again, and voila, it works. And how does it work? Well, to cut the long story short, basically we use some compile hooks that are defined by Elixir. Gradient provides implementation of these hooks, and for as long as we use well-defined and a bit limited request data, like ecorec, or in general tagged tuples, and also we use this macro for sending the responses, we will get these auxiliary functions generated. And I think that's really all I wanted to show as the demo. So, yeah, thanks for joining, thanks for listening, and one more thing, we, that is Erlang Solutions, are hiring. So if you're interested, give us a shout at our emails or check out erlangsolutions.com/careers. And that's it. Thank you.
Are there any questions? Oh, there's one.
So I have two questions. The first one is related to the performance. Is there any performance overhead related to using Gradualizer? And the second one is related, because I saw that Gradualizer is pretty popular on GitHub. Did Gradualizer get an interest from the Erlang core team?
Okay, so with regard to the first question, no, there is no performance overhead because there is actually nothing happening in runtime. It's a completely build time or compile time tool. So I would say, if you know Credo, which is the linter for Elixir, it's similar to that. You run it on your source code, you get some feedback, you use this feedback or not, but there's nothing extra happening at runtime. So no overhead. With regard to interest from the OTP team, I have to admit that these tools are still pretty experimental. So with regard to Dialyzer, for example, which is quite stable, but also is not necessarily intuitive. Like, we would want it to tell us more things or be more specific, but it doesn't, let's say, it doesn't lie. If it says something, there is a bug in our code, or there is a bug in some macro that we use in Elixir, because macros are a bit problematic sometimes for it. So with regard to Gradualizer and Gradient, these tools are still in development. They might give false positives. There was interest, there is some interest from the OTP team, but it's still early interest, like when could they use it for OTP? So for example, we were doing some tests on OTP code. We still see some issues with testing OTP code. And these are probably a little bit of type issues in the code itself, but these are also issues with the tools too. So we're getting there.
So the first question is related to the previous demo you showed. Can you show it again, please?
Yeah. Just which one?
Yeah,
or any?
The place where you're using the type server.reply.
Yeah.
Because the question is, can't we return a regular reply tuple instead of using type server.reply and providing a proper type spec for the handle message so that it, for example, returns the reply tuple instead of just state and using type server reply?
Okay, so there are two aspects to this question. The first one is, could I just return a value from the handle function? This depends on how sophisticated this extra glue code and gradient is. So if we make it sophisticated enough, we could do it. Let's say it's pretty simple so far, so we cannot do it. With regard to the second aspect, could I wrap this, could I have that information in the handle function? I am not sure at this point. Maybe, but I am not 100% sure, because this function returns some control data, some control structure to the GenServer framework. And it's not necessarily the same thing as the type of the response that we send with GenServer reply or type server reply. Although one of these, one of the variants of this control structure has the type, might have the type of the return value. Actually, this is a good question. I would have to think a bit more about it. It doesn't seem to.
Anyway, I guess the returning the tuple is a bit more intuitive than using the reply. That's why I asked the question.
Yeah.
Yeah, and another question is, you said that you're heading there. I mean, to I guess being quite stable, and the question is, how far is it? Can you estimate? And is there any way that usual user of Elixir can help in that?
Okay, so how far it is from being stable? That's a bit hard to answer because there is not a lot of people involved in these projects. Practically, there are 3 people that are somewhat active, but they are not full-time on these projects. So we could say that the development is actually best effort. And the problem domain, while interesting, is also quite complex. So one thing that's certain is that Gradualizer is not complete. Like there is a known chunk of let's say, the theoretical model that should be there, but is not there, which is called a constraint solver. So for example, when we have some polymorphic functions, we will not get warnings. Even if you read the spec, you think that, okay, I know what it means. The type checker doesn't. It will not give an appropriate warning. And then there are the more practical things. So we just run it over real-world code, and we get some warnings which are valid, and we get some warnings which are false positives. And, well, there are still cases of this happening. So it's a bit more about just engineering and wrenching on the code to fix such cases. I wouldn't say it's stable yet or like complete yet, but on the other hand, there is no risk of breaking anything because you don't ship it with the production release. You don't run it in production. There's nothing to run in production. So in the worst case, you can just get an output that's not completely accurate. In the best case, though, it might tell you about some issues in your code.
Great. So if you, for example, used it and ran it on a pretty large code base, for example, and we, for example, figured out some inaccurate advices there, is that helpful for the development?
Yes, it would be helpful. If you do anything like this, please let us know on Gradient or Gradualizer issue trackers. That would be great.
Great, thanks a lot.
Thank you.
Okay, are there any other questions? Because yeah, I have one more. The first one, you were showing the code and run the type check from the console. Is it ready? Does the gradient have the mixed task for it, like to run it outside of the IX?
Yes, there is a mixed task available. You can run it on an Elixir project. We're also thinking of having a standalone script like xdoc, but it's on the roadmap. It's not ready yet. So it would just allow to install the thing and run it on, for example, single files to single out errors. Okay,
and one more question. Is it possible to gradually introduce the Gradualizer into the code base? How does it cooperate with the dialyzer?
So, as the name implies, it is. Basically, the assumption is that if there are no specs, there is no type checking. There is a little bit of inference going on. So, for example, when you build a struct or a map, it will infer that the type of such constructs. Or if you use like addition operator, it assumes that the operand should be integers. But in general, if there is no spec, there is no check. So it's possible to introduce checking gradually. You just add more specs to your code base, and the more specs there are, the more checking takes place, and also the more specs there are, the better are the results, because like the functions are more consistent because of the specs linking them. So yes, it's possible to do it gradually, function by function. With regard to compatibility with Dialyzer, We're not aware of any incompatibilities at this point, although the models, like the theory behind the tools, is very different. So there is no guarantee that at some point in the future they will be 100% compatible. It might be the case that something will type check in one, but will not in the other. But I'm not aware of any such things yet.
Okay, thank you.
Thank you.
So thanks for your presentation once again. And now is the time for our final presentation today. Like seeing your presentation, of course, I was reminded that I have to say that we're also hiring. So feel free to visit our site for that. And right now is the time for more of a membrane during this meetup. It will be presented by Dima, and Dima will show you his latest addition to the membrane framework, which is ability to capture the video from a camera and stream it. Okay, so if you're ready, you can start them.
Okay, so hi everybody. My name is Dima, and I am a software engineer intern at Software Mention. I was working on Membrane, and today I'll try to introduce you to multimedia processing and to Membrane framework. We'll do that on a simple example. The idea of this example is to be really simple as possible, and to capture natively video from the device's camera and convert it to HLS stream. And I'll try to be as I'll try to put things out as simple as possible, just for everybody to understand and to be able to catch these slides. So first of all, one more time, we'll capture the video, we'll convert, we'll do all this stuff, the interesting stuff which is going behind the scenes, and just stream it out using HLS. So what is HLS? HLS is an HTTP-based adaptive bitrate streaming communication protocol developed by Apple. It's just, it can traverse any firewall because it just uses the simple HTTP traffic. And you can just stream your content using the content delivery network. And this is the benefits of HLS. And there, in this slide, you can see how HLS works. You just capture the video and an audio. You encode and segment these streams. Then you can distribute your files by division these files into some chunks. And these divided chunks can later be served to a client. So we have a playlist where we define these these media types, and we have some segments. Simply put, this master playlist just defines, for example, different video qualities. We can have some cellular video, we can have some Wi-Fi video, we can have full HD videos, and each of these media playlists can have its own media segments. And these media segments are just some files, some, for example, 2 or 5 seconds long videos or audios, which can then be just served using just HTTP. So the process, the pipeline, or the stream that we would like to proceed is the following. First, we have the source. In the source, we just capture the video. Then we have a pixel converter, because we'll describe it later in more detail. But now the source just captures the video. Pixel converter converts the pixels, changes the format of the images that we receive from our camera, for example. Then we need to encode this and parse. I'll show and describe later what is encoding and what is parsing. And then we can just use HLS to divide these encoded files and stream it out using HLS. So, source is the simplest part of it. We just capture this video. We got raw video frames. Depending on operation system, we can have an RGB files, like RGB format, or some others. And now I'll tell you what is an RGB. I'll try to tell you what is an RGB, because the converter, after we captured the video, we need to convert it. Because some popular formats use I420, not an RGB. RGB is just red, green, and blue. We have 24 bits for each pixel. And we can have as many pixels as we want. But it's too much. Because of that, and because of people who perceive wider brightness range than color range, we don't need to store so much data on colors. We can store just the brightness and some blue and red colors. For that, this format was created, and it reduced size from 24 bits to 12 bits. Yeah, and there we can see a picture where the first one is just the real image. The second one is the only luminance, brightness, and then we have blue and red, which are stored just in 2 bits. And it's single. Every pixel has this amount of bits. After we have source, we have converter. We have converted our source, our pixel formats. We need to encode it. What is encoding in the media? Encoding is just taking the raw video in some pixel format and converting it, for describing some dependencies between some frames, because video is just a sequence of these frames. By frame, I mean just images. Video is a sequence of images, and encoding can do some video compression, because not every image is different from each other. There are some dependencies. For example, the third frame can depend on the previous or the next frames, and because of that, we can just compress this, not to store each image by itself, but compress it. And this is what encoder function is. It just converts raw video to some digital files, so it's not saved as individual images, but as a fluid video with some dependencies between these images and some complicated mathematical compression. And this provides us to some video compression standard. This is what H264 is. It's it has 3 types of frames, and it's pretty common to have 3 types of frames. The first type is iframe. It's just an image which has all of the information needed to show. For example, when you have this image, you can just simply put it on the screen. We have P frames. These frames predict its state on the basis of the previous frames. As you can see in this picture, P frames only show on the past frames, on the past E frames or some other frames. And we have B frames, which can use both previous and future frames to predict its state. So when you have some sequence of frames, you can display each frame simultaneously. You need to display this frame and the other frame, and because of that, you can have some data to display, you can have some future data, and you can use this data to just compress this image. And this is what encoder does. It just converts our sequence of images to this compression standard. The next thing is a video parser. Video parser is responsible for generating metadata and timestamps based on the specified frame rate, for example. What does it mean? Generating metadata is just putting to each frame, for example, the time where it can be shown. If you have 30 frames per second, it means that when we receive this stream, each frame is like marked with this timestamp, and the browser or the client can have like can easily understand where and when to put this frame. And this is what the function of video parser is. There we can have some parameters like to deliver some more frames or less frames, but it's not really important now. And the second and the last part of our pipeline is just HLS sync. It performs payloading and muxing. It's not really important now what it is. And it just generates these playlists and persists them in the storage. So it divides this chunk into some smaller chunks of the video and puts these playlists and manifest files, and then they can be served. And there we have a cool slide which tells how Membrane works and for what Membrane was created. Membrane has more than 178 packages and plugins to help you do all of the things that I've mentioned above. And the level of understanding which I've provided is enough to use these elements. Membrane can be used as an abstraction to multimedia processing. We don't need to understand all the details of how the multimedia is processed under the hood. We just need to understand that one thing is coming after another thing, and we need to pass some parameters for it to work properly. We can gain all of the benefits of the functional programming because Membrane framework is written in Elixir, which is based on Erlang OTP, and because of that, we can just convert our vision, like these 5 bullet points, to just pipeline, and simply perform all of the action using this simple pipeline. So Membrane, going into some detail, Membrane has elements, which are just these source, converter, encoder, parser, and many others. This is just elements. This is just Membrane elements. Membrane has input and output paths, which are just capabilities. They just define a type of data that this element can receive, and the type of data which this element can output. And because of that, and the last part of Membrane is pipelines. Pipelines are just the connection of these elements. So we define the order by which these elements interact with each other, like pass some data and so on. So Membrane, just simply put, has 4 big parts, big parts that it has. It's just elements, paths, some capabilities, and pipelines. Capabilities are just like specs for an Elixir function. That's it. And I'll show you now how easy this vision can be converted to the code. So we have a live coding session now. So I'll open an editor, and you should see the simple application, Elixir application, which starts the pipeline, which I defined there. It just, in future versions, startlink and pipeline play. Startlink will do the playing, will do the converting to the state of playing. But for us now, it's really important that just pipeline play will initiate the handle init, and we'll link all of the elements that we define in children, and in the order that is defined in links. So all of our work there is just to define these elements and link them together. So, first element that we saw is just source. So let's define it. Source, it's membrane camera capture plugin without parameters. And that's it. That's the first element. The second element, according to the presentation, was a converter to the format I420. So let's define it. Converter to the, it will be membrane FFmpeg, because membrane under the hood uses just FFmpeg. In some cases, as for scale, pixel format converter, and there we need to pass a format which is I420. Yep, so we have our converter, and the next part is encoder and parser. So encoder, it's a membrane encoder. No, FFmpeg encoder, FFmpeg encoder. And there we need to specify the profile of the encoder. I've told about parameters, and that you need to know what things you are using. So what is profile? Profile baseline is just a profile which tells our encoder the way that it needs to encode the video. In this particular case, we need to ignore B-frames, because the usage of it will be in browser, and we won't be able to look into the future, because B-frames are just using the frames from the future, and we can not always have them. But we just use baseline profile, which ignores these frames by default. And then we need to implement our parser. It will be membrane H2 for FFmpeg parser. And there we need to pass additional parameters. It's a frame rate. Frame rate will be 30 to 1 frame, I guess. That's the way it works. Alignment will be AU. It means that we'll transport 1 frame per null. Null is the unit of transportation, and it also is needed by the browser to work for everything to work correctly. Let's put it that way. And we need to attach this. Let's just put it through. And I want to underline that this part is these parameters are not just important. You can just simply search the repos, and all the way they are used pretty much the same. And if you don't want to go into the detail, if you don't need to go into the detail, then you can just use them that way. And the last part, according to the presentation, was just our AHLS. Let's call it AHLS. And it will be HLS sync bin, because it just uses it does payloading and muxing, and because of that we can use the sync bin. For it to be simpler, we just use membrane HTTP adaptive stream, and there's sync bin, and that's And there we need to specify the manifest module for it to be HLS. So it will be just membrane HTTP adaptive stream and HLS. And we need to specify the storage. The storage is just a direction of the files, of the output files. and we need to call it like output. It will be membrane storage, I guess. Yes, membrane file storage, storages, file storage. And there we pass directory output. Yes. And that's pretty much it. So we have our children, we have our elements. And now we need to connect these elements into a pipeline for everything to work. And that's really easy. We just put link. There we pass an atom source. And we have a pipeline. So we pass our source to the converter. Converter. Then we pass it to the encoder. I'll copy just. We'll pass it to the encoder. We'll pass it to parser. And we just need to pass it to the HLS sync. But in this part, it's not that easy because HLS sync has some parameters on its paths. And we need to use something called via in. And there we just specify that it's an input path and specify its options. We need to specify that encoding will be H264. And we can specify the track name there. Track name. My track name. And we pass it to our HLS. Yep, that's it. So we have our elements. We've connected our elements. It's just a simple pipeline. From the source, data goes straight out to our HLS, which then will generate the output file. And we can test it out, how it works. So we just go and run mix run. And there we need to have an output data. After some time, it should appear if everything is done correctly. Cool, it's not working. I don't know why. Should, probably. So we have source, converter, encoder, parser. Everything looks fine. I'll just allow myself to check out to the previous branch. Have no idea why it's not working. But simply put, we have our camera capture, like source. We have our converter. We have our encoder. We have our parser, which has a frame rate, alignment, and attach nailers. And we have our sync, like sync bin. And we have these links. Let's check it out whether this version is working. Probably yes. No, it is still not working, and I think that the problem is with this HDMI, because it works, it doesn't crash, but it can capture the camera. So I try to unpin, and yeah, and then it works. So it wasn't my fault, completely. I've done everything right. You need to trust me that now the camera is capturing the video, and you can see yourself there. And I'll connect one more time and just put it off. For you to see everything, probably you should see now. Yes. So, we've recorded some video. The problem is that this adapter just somehow captures my camera and is not allowing me to use it. I don't know why. It wasn't tested. But we can see that our index file is generated. Our track, our index file, is pointing to our track, which is first track. Let's go to the first track. And this track has some segments. He's pointing out for all of the segments. It shows the length of the segments. That's it. And it shows the name of these segments, like M4S. We won't be able to open this file, but it's just the video that we're looking for. So now we need to open this video. I've wrote previously a simple HTML script which uses a HLS.js library to just, what this script does, he just asks the server, like each time, each X seconds, and gets these tracks. First of all, he gets the index file, the index M3U8. Then, by this index, he understands the quality of the files that he needs, and he just asks the server to give him these files. And we can use a simple Python file server, HTTP server, which will serve our files. So if we ask for a file, we get the file, and then go to the browser, go to our localhost stream, I guess. Yeah, and we have this video, which we've recorded when I've just plugged out the HDMI, and probably you will see yourself in some time, I think. Yes, so it works. And I think that's pretty much it on how it works. Let's come back to the presentation. So is everything clear? Okay, I'm glad that everything is clear. Let's go to the last slide. Probably I've had something there. Nope, nothing. So I think that by the end of my speech, not the most successful one, but you've understand how just membrane works, how it's easy to having some small knowledge on the media, which I possess. You can just use everything that membrane provides to you, and it works. It just works, and it's really easy to implement everything. So that's probably it from me. Thanks a lot. Do you have any questions?
Thank you very much. I'll just do it without the mic. Thanks a lot, Dima. That's it for our presentation today. Yeah. That's it for our presentation today. And now is thanks for watching us to those who were online, and those who are at the office. Now is the time for the fun part. I think we have some Elixir over there that we might try, and as far as I can tell, the pizza should arrive soon. So thanks for joining us, and enjoy the rest of the evening. Thanks.
Publiczne, możesz zamknąć.